software fixes. Okay, yeah, it's a little better, but guess what? There's the next bottleneck. Oh, let's patch that. Let's throw some more hardware at it. Nope. There's the next bottleneck. We have an expression for this in the United States called peeling the onion. You know, instead of slicing right through the onion, you're going through one layer at a time. And what are you doing if you're peeling an onion? Crying. Right? Yes, you're crying. There was a lot of crying. A lot of wailing and gnashing of teeth. And ultimately the project failed because of these performance problems. Okay? Again, these were predicted 18 months in advance of us seeing them in test. Somebody showed us a spreadsheet. These are the things you've got to watch out for. Now, how sad is that? To work on a project where you knew what could have happened, and you just, people didn't follow up on it, right? And it's not one, I can't point at one person, that's the bad person. We all dropped it. Okay? We all should have been on top of this stuff. We're talking about a 2-year project. It had about 100 people on it. We're talking 200 person years of effort lost, wasted. That's sad. Okay, so what could this project have looked like? Well, we saw another example of it, a subsequent project. Again, we got a spreadsheet doing modeling of the resource utilization. And guess what? Instead of ignoring it, design changes were made based on predicted problems until the spreadsheet said, okay, this will work. We're looking good. Then they created a simulation using a tool that's currently called Hyperformix. Some of you might have heard of it. And they were able to run simulations. Found more problems with the design. Fine-tuned the design some more. Notice that at this point there isn't even any hardware or software. It's just a design. As they started to create the hardware and software, there was performance testing at the unit and subsystem level, and that was compared against the simulation. Problems were found in the simulation, problems were found in the implementation, those were fixed. Okay, so once we got into system test, for the most part, the simulation and what we saw and what we wanted to see were matched. Okay? Let me show you an example. Pardon me. Simulation. The simulation for the IMAP server, which is the email server, predicted 45% server utilization of 25,000 users. Okay, that's the prediction of the simulation. We got 2 servers here with load balancing, simulated load of 25,000 users. Look at that. 45% and 41%. Right? 100% minus 59, 100% minus 55. That's pretty good, huh? So we simulated it, we built it, we iteratively refined the simulation based on what was seen as it was being built, and then when we tested it, we found a few problems, but nothing showstopping, nothing fatal to the project. If you want some more details on how we did this, if you go out to the rbcs-us.com basic library page, there's an article called The Right Stuff out there that describes how this process worked. What does this require? Again, discipline. I'm not talking about anything that we can't do. We know how to do this. And we've known that we should do this for a long time. A lot of these concepts stretch all the way back to Fred Brooks, the mythical man month. But the difference between this project and the project I was just talking about, the failed project, discipline. Doing what we already, as an industry, know that we should do. Okay, another lesson here. Stuff needs to work together, right? Stuff needs to work together. And that's just going to get more and more true, isn't it? Everything is connected to everything else. I mean, I can do phone web-based banking on my phone now. I can go out, this thing runs Safari, I can access my bank account. So what do we got? We got software running on an iPhone, talking to COBOL on a mainframe. And I can guarantee you that when the guys writing that software for the mainframe wrote it, somebody said, yeah, someday, about 30 years from now, somebody's going to have this phone and it's going to have an internet browser on it and he's going to be using it to transfer money. And those people would have looked at that person and said, where did you come from? Mars? What's the internet? Handheld phone? Right? So everything has to talk to everything else. So this is a challenge for us because just because things work by themselves doesn't mean that they're going to work together. And just because older versions of things work doesn't mean that newer versions of things will work together. And quality risks can compound. You can have a small problem in one component that once it gets down to the other components that it's talking to, that is magnified as a big problem. So, we got to test control flows and data flows across interfaces. We've got to make sure that stuff works together. We got to use continuous integration to make sure that when we break builds or we break interfaces, we found it quick. Now, some people associate continuous integration with agile and iterative. No. This is an idea that's been out there for a long time. And again, it's discipline. It's doing it. Automated unit testing frameworks. Let's use these, and not just for component testing. Let's use them for integration testing. Let's not wait until the end to find integration problems. Okay, so famous example of not thinking about, not thinking about integration. An Ariane 5 rocket. Right? Some of you know this story. Basically, there was a reuse of a piece of software from a previous version, the Ariane 4, and there was an issue with 64-bit floating point versus 16-bit integer, and that was an attempt to share data between two software components, incompatible data types. And so one piece of software got confused. And what happened? Some of you have seen this video. If not, you can go out and take a look at it. I don't want to spend time running it now, but basically the rocket goes up and it starts to tip over because of the miscommunication between these two pieces of software. And at one point you can see it's almost completely sideways, and then they hit the self-destruct button on this thing. And we're talking about $500 million blown up. Oops. How hard would that have been? How hard would it have been to run that integration test? Not very hard. Certainly wouldn't have cost $500 million. And, keep in mind, this was actually a best case outcome. Once they hit the launch button, the best thing that could have happened was $500 million exploded in the air. Super expensive fireworks show. And the worst thing that could have happened is they could have failed to destruct it, and it could have come down and killed some number of people. Now, fortunately, we're talking about French Guiana, where it's launched, so there's limits on how much damage that can be done. But still, there could have been people killed. Mission happening in this system, so somebody writes code, and when it's done, they check it in, and it's integrated with everything else, and then everything happens periodically, every 4 hours. All of the unit tests, all of the component tests, all of the integration tests are rerun against the code base after checking it's happened. Again, more detailed description of how we did this in the article called Mission Made Possible on our basic library page, but just a quick overview. Here we see the programmers are creating Java code and JUnit unit component integration tests in their daily development. This is just standard Agile stuff here, right? The test-driven development type of thing happening. Okay. Which, by the way, is not new to Agile.